Hi there. This is a reinforcement learning project presentation, which was based on a paper by Ian Xiao called a distributed reinforcement learning solution with knowledge transfer capability for a bike rebalancing problem. In this presentation, we've discussed the overview of city bike, the environment and problem, solving the problem, comparing results we had, comparing the best methods, and finally recommending the next steps. One of the bike sharing programs in New York City is called City Bike, which became very popular over the last few years. Very convenient, they have over 800 stations. The key problem is that they have a lot of uneven bike distributions across the stations, which means one location could be full of bikes with no space to park, while another station could be sitting empty with no bicycle to rent out. It's costly to have too many bikes or not enough bikes in a location. This problem is solved by human employees who use a van to redistribute bikes, which is not very efficient. So we use reinforcement learning to solve the problem. How many bikes should be removed or added per hour from a location to achieve an optimal bike stock over a 24-hour period? We've chosen a location near a Central Park. We presume that it would be a busy and popular station, so it would make the challenge more interesting. Our state transition, which is the net expected stock, to make this as real as possible, we've used Citybike's historical data from June to August of 2019 for every hour of the day. In our action space, we have three action sets: either add bikes, remove bikes, or do nothing at every hour. Our reward function depends on the stock per hour and movement of bikes per hour as well. Looking at our chosen location near Central Park, this station has a maximum capacity of 45 bikes, which means that overstock would be above 45 and understock is 0 or below. We've also assumed that the starting number of bikes is 20 at every episode, where one episode equals 24 steps for the agent, corresponding to the 24 hours of a day. And we reset the starting bike to 20 at the start of every episode. Our stock per hour is the difference between the number of bikes arriving and number of bikes leaving the station. To get the number of arriving bikes, we took the historical mean and standard deviation for every hour, shown by the orange dots. To limit the variance, we've used the mean and max of the number of bikes arriving per hour, which is represented by the black lines. We've also performed the same steps to get the number of bikes leaving by getting the historical mean, standard deviation, mean, and max. And the difference between the arriving and leaving bikes gives the net expected stock. In terms of the action set, we wanted it to be reflected of the expected stock, which is quite random. So we initially considered having a smaller number of bikes in the action set, but it won't be effective. For example, moving one or two or five bikes per hour when we know that the stock can be in the tens or twenties is not the best thing that the agent can do. So we came up with seven possible actions per hour, which is add or remove 30, 20, or 10 bikes or do nothing. Even though our maximum number of bikes for our location is 45, we've set our threshold between 5 to 40 bikes to ensure a minimum number of bikes and parking spots at the station. In terms of the reward points, we gave the agent a negative zero point 0.5 point for every bike moved per hour. This is to minimize the movement of bikes. The agent would also receive a negative 30 reward points if the threshold is not met at the end of every hour, or 0 if the stock is within the threshold at the end of every hour. We've used reinforcement learning algorithms, which are Q-learning and SARSA. We've also considered a few hyperparameters, epsilon of zero point 0.1 and 0.01 to test how greedy or exploratory the agent would be, discount factor of zero point 0.9 and zero point 0.1, and we trained the agent between 100 and 20,000 episodes. For evaluation, we've used the session success rate, which is the number of episodes where stock was within threshold divided by the total episode count, the average reward per session, and the stock history, which showed the first and last episodes about how the agent performed. We started the approach by first using Q-learning, which is our base method. Then we compared it with a random policy and a do-nothing policy. Finally, we compared it with SARSA. And then we tuned one hyperparameter at a time to see the differences. Our base method, which is Q-learning, where we first experimented on the different episode counts 100, 1000, 5000, and 10,000. As the graph shows, the rewards improve as the number of episodes increase, which tells us that the agent is learning when performing more episodes. From 100 episodes having a reward of negative 325 to above negative 200 with 10,000 episodes. This is also confirmed by the success rate, which is the blue line on the graph, from 77% at 100 episodes to around 90% with 10,000 episodes. Looking at the stock history of our base method, at episode 0, the stock varied widely. The agent was still learning to counteract the variations in order to be within the threshold. The orange line represents the stock movement, and the black bars represent the actions taken by the agent. Looking at the graph for episode 10,000, which is more harmonized, the agent has already learned to perform the correct actions. When the stock dipped outside the threshold, the interesting part here is that the agent did nothing when the stock was within the threshold. We've also experimented with a no-action policy, which means we've restricted the agent to perform nothing, whether the stock went outside the threshold. As we can see here, the rewards shown by the blue bars hover at around negative 325 points. There is no improvement whatever the number of episodes. This is corroborated by the success rate, as we see here. The success rate for a no-action policy is just around 62%. And looking at the stock history for a no-action policy for the last episode, as we can see here, as the days progressed, even if the stock was already threading in the negative values, the agent couldn't do anything. Thus, it cannot rectify the situation. We've also experimented with a random action policy, setting the epsilon value at 0.9. This means that 90% of the time, the agent is allowed to explore alternative actions. Similar with the no action policy, the reward points hover lower at around negative 450 points. No improvement from 100 episodes to 10,000 episodes significantly. This is supported by the success rate, as we see here. The success rate for the random action policy resulted at around 72%, which is a little bit higher than the no action policy. This is because the agent was able to apply some corrective actions when the stock went outside the threshold. Looking at the stock history for the random action policy, we can see here that the agent took some corrective actions due to his exploratory behavior, even if those were not optimal. The second algorithm we've experimented on was SARSA. Resetting our epsilon to 0.1 for fewer episodes, our SARSA outperformed Q-learning. But as the episodes increased, Q-learning outperformed SARSA a little bit. This is confirmed by the success rate. From 77% at few episodes, the success rate went to as high as almost 90% with more episodes. Checking the stock history for SARSA, on the first episode, when the agent was still learning, the interesting point to see here is that when the agent learned what action to perform, it generally did nothing when the stock was stable or within the limits. Now to glide through the summary of our results, this shows the comparison of average rewards and session success for epsilon 0.1, which is our base, and 0.01. This slide we show the comparison of average rewards and session success for epsilon 0.1 and 0.01 for SARSA. This slide, we show the comparison of Q-learning versus SARSA for discount factor of zero point 0.9 and zero point 0.1, as well as the average rewards per episode count and the session success for Q-learning. And on this slide, we show for SARSA as well. Now on this slide, we show here the summary of different experiments we performed using different hyperparameters and their corresponding success rate results, of which the highest success rate we got was 90.7% for Q-learning having an epsilon of 0.01, discount factor of zero point 0.9, learning rate of 0.01 at 20,000 episodes. This slide, we're just showing the value of our Q table, the stack count on the horizontal axis, and the hours on the vertical axis. Now, this slide is an overall recap for Q-learning, showing the different success rates for each policy. So finally, our recommendation to further improve the performance of the agent. In the future, for the stack count, there could be no reset or starting with different stack counts and scale up to a year instead of just daily. The reward function could be modified to include the time of the day as well, or setting different thresholds for every hour. And finally, aside from Q-learning and SARSA algorithms, Deep Q network or Monte Carlo could also be tested. And that concludes our reinforcement learning project presentation. Thank you.